Alright, we're now going to talk about blackbody radiation. And the idea is if the object is perfectly black, right, the reason we have colors, the reason this eraser is blue, because the white light in the room coming from the light bulbs, all the white light hits it, but it reflects off just the blue part of the spectrum. And that reflects out, goes to our eyes, and sets off our blue detectors. Okay? So it's absorbing all the other colors, but reflecting off the blue light. Well, the idea is if you have something that's perfectly black, then it's absorbing all the light that's hitting it. And so it's a perfect absorber, absorbs all of it and collects all that energy. Remember, light is just energy, so it's absorbing all that energy. Then it re-emits it depending on its temperature. What that means is this. If we plot this, like this. We're down here, this is the light. And I'm going to put over here, I'm going to put a violet light here. And red over on this side. So this is the visible part of the spectrum here. This is infrared over here. This is ultraviolet over here. This is the amount of energy that's output by a black body object depending on its temperature. But first let's talk about temperature scales. Alright, now the one that we use is the Fahrenheit scale, which is by far the worst of all of them, which is typical, I guess. We get something and we never change, even though there's way better ones out there. The Fahrenheit scale says that where water freezes is 32 degrees. And in the Celsius scale, or the centigrade scale, they set that to 0. And then when you go to water boils, or changes state here, for Fahrenheit scale that's 212 degrees. For Celsius that's 100 degrees. Okay? And so that made a whole lot more sense to do it in scale of 100, so that's why Celsius was created. Fahrenheit was a German who invented a thermometer. And how he came up with water freezes at 32 was he actually just measured the temperature one winter in Germany. And the coldest day that year he called 0. And then on the scales that he had marked on his thing, 32 just happened to be where water freezes. So it was not based on anything, it was just random, okay? Now, what is temperature? What really is temperature? Temperature is a measure of the internal energy of an atom or a molecule or a gas, the way they're bouncing together. So if you lower the energy, so you get something colder, then you lower the vibrations, you drop all the electrons and everything to their lower states, and you get it colder and colder. Essentially, you get everything at its bottom energy level, which it rarely ever is. But there is a point where if you keep it colder and colder, there is a point where you can't get it any colder, where everything is at the bottom energy level, and it can't get any colder than that. We call that absolute 0. And that is at minus 273.16 something degrees, okay, in Celsius. I don't even know what it is in Fahrenheit. Nobody deals with that. And there are people that deal with this, that deal with the really cold, the cryogenics. And there's a couple of groups that are in the world that are trying to beat somebody. So they say, oh, we got it down to 1/1000th of a degree above absolute 0. And then the other group halfway around the world, no, well, we got it to 1/10,000th of a degree. And so they try to go for the absolute cold. And weird things happen as you get close to absolute 0. We find there's all kinds of new different states of matter. Like we talk about solid, liquid, and gas, and that's it. No, there are all different kinds of states of matter, especially when you get to these extreme temperatures, which are really cold. Well, Lord Kelvin actually was a lord. He said, oh, let's do this more logically. If this is absolute 0, let's call that 0. Then all temperatures should be positive. There will be no negative temperatures because you can't get below 0, so everything is a positive temperature. Which is true in the universe. The lowest point should be 0 and energy should go up from there. And then what happens is you go up to water freezing. Well, water freezes at 273 because it's the same size differences for each temperature as the Celsius scale, and water boils at 373 degrees. Okay? So when I talk about temperatures, I'm going to talk about temperatures in Kelvin because that's pretty much all astronomers usually use. Now let's think about this. What's the human temperature in Kelvin? Well, most people realize that it's between water freezing and water boiling. Since you're made of water, we want our water to be liquid inside of us. We're at about 98.6 degrees on average, the human. Well, that puts you in about 30-some degrees here, about 35 degrees in Celsius. Well, that puts you at about 300 degrees, 300 to 310 degrees Kelvin. So everything has a temperature of 300. All humans have a temperature around 300 degrees Kelvin. All right, so we go back to our blackbody radiation. If I have a star like the sun, a star like the sun gives off most of its energy, and it goes like this. And the sun has a surface temperature, that should be nice and smooth, but you get the idea, of about 5,800 degrees Kelvin. Let me extend this. So this is the visible part of the spectrum right here. And so it's got a blackbody curve like that. It gives off light. If we keep going over here, this is infrared, this is radio over here. It gives off most of its energy in the visible part of the spectrum. Exactly where our eyes can see. That's not chance. It's because our eyes have evolved to match the star that we're on. Our sun gives off most of its energy right here, so our eyes became sensitive to that exact region of the electromagnetic spectrum. If we found aliens living around some other star, then that star was a lot colder. If it's a lot colder, like a couple thousand degrees, it looks like this. And it gives off almost no ultraviolet light, no light up here. Most of its light is off here in the infrared. You get some in the visible, but it's going to be a lot more red than the rest. And so this star would appear red. So a red star is a lot cooler than the sun. Now the sun, notice, gives off almost the same energy all the way across. With the same energy all the way across, it's going to appear pretty much white. And they say if you're up in space, away from our atmosphere, the sun appears pretty much exactly perfectly white. We get a tinge of yellowish color here because we scatter out the blue light coming from the sun, which is why we have blue skies. But the rest of the light gets through, and so that makes it lean towards the yellow side of the spectrum. All right, and if we have a really hot star out here, it peaks up here. This would be a star about 20,000 degrees Kelvin. Notice it gives off way more energy than the sun or the red star. So it's very hot. And most of its energy is pushed over here in the visible part of the spectrum. You get a lot more blue than red light coming out. So this star would appear blue. So a blue star is very hot. White star like our sun is middle, and a red star would be very cool. Notice it also gives off massive amounts of ultraviolet light. Now, let's think about this from finding life for other planets. If you find a star like this, we think it's less likely for life to exist around that, on a planet around that, because it's pumping out so much nasty ultraviolet radiation. This stuff is really bad for life, like we know it on Earth. And so it's much more likely that life wouldn't be there, meaning the planets would be sterilized by the star. Cool stars, they have a problem too. If they don't give enough energy in the upper part of the spectrum right here, then plants can't have photosynthesis. You can't photosynthesis occurring down here because the energy from the sunlight has to be strong enough to allow the plants to absorb that to produce more plant material. And so red stars may have a different problem in that they don't have enough of this. So really we think that the stars that are looking for life like we see it on Earth, we only have one example, need to be stars that are within a range close to the sun, which is why we're here. All right, let's put humans up here. Because humans, we decided, are about 310 degrees Kelvin. Hey, we do give off light. Everything in the universe gives off light. We give off light down here. Meaning we give off our light in the infrared. Which is why if you have an infrared detector, like the military uses, you can look at night and you can see all the humans glowing and everybody looks kind of weird in the infrared. That's because you're giving off infrared radiation. Everything with a temperature in the universe gives off some form of radiation. And so, that's why we can detect it. So any matter out there, we can detect it if we look at the right wavelength. The very coolest stuff in the universe, we look in the radio waves. As we get hotter, we shift over. So things about 300 degrees, you're in infrared. Thousands of degrees, you get into visible light. You get up to millions of degrees, you get into X-rays. You get up to billions of degrees, you're into gamma rays. So what temperature an object is depends on what wavelength it's going to give off for the most part. And that's the whole idea behind infrared radiation. This is just a light bulb here. And I don't know if you'll be able to see this demonstration very good in here, but I'm going to give it a try anyway. But I can adjust the voltage going through there. Essentially, it's adjusting the temperature of the filament. This acts just like a black body. In fact, it is a black body giving off light. It's a little filament wire, and you see as I turn it down, it turns orangish color. I'm shifting it over here to orange. Okay? And as I turn up the voltage, it shifts from orange to yellow to pretty much white. We're shifting it over here to the spectrum. That actually